Yeah, thank you for the introduction and the support. As has been mentioned, my name is Alexander Schlosser. I'm from the group of Professor Ricoeur in Kassel, Germany, and I will talk about matrix and interface cracks in multiferroics. Of course, this is a really broad topic which won't fit in 12 minutes, so we will focus on, or I will focus on one specific, rather interesting detail in this. And I will start with a few motivational words about multiferroics. What are they? What can they do? And basically, multiferroics are materials or composites which are able to perform the magnetoelectric effect, and that is coupling electric and magnetic fields or vice versa, and so to transform signals. And without being a result of the Maxwell equations, it's a pure material property. And this leads to many interesting applications like sensors, transducers, data storage devices, you name it. There are many ideas, novel actuators are a thing. And as I said, they are mostly constructed as composites like particle composites, fibers, or laminates. There are a few monomaterials which can exhibit the effect, but they usually function at non-interesting temperatures like minus 200 degrees Celsius or something like that. And the components of those composites are usually brittle ceramics, like we heard about vinyl titanate, piezoelectric. That's one candidate for it. And brittle ceramics means we need to take into account cracks and fracture. And there's a little overview over the fracture mechanics in such composites or in situations is as follows. So it's brittle, so you're linear elastic in most cases, but on top of this you have, for example, magnetic and electric loads, so fields inside the electric and magnetic fields, which are shown here in blue, which are inside those materials, which might penetrate the cracks and so on and so on. You have anisotropy we heard about, interface cracks, interfaces everywhere, and on top of all of this you have electromagnetic forces, which act on the one side as surface tractions. I depicted them here at the crack faces. They also might be here at the interfaces. And you have electromagnetic body forces too. So they belong together, as you will see in a few slides. And these surface tractions at the crack faces have been taken into account in quite a few publications, but as far as I know, of course, these body forces haven't been taken into account too much, the results of them. And that is, these body forces are what we will look at in the next 10-ish minutes. A few more detailed words about those electrostatic forces. So as I said, you have surface tractions which are defined like this. The big Tij, the capital Tij is the Maxwell stress tensor. And yes, these tractions at interface are defined as a jump of this Maxwell stress tensor. And the body forces are defined as the divergence of this tensor. So they are both defined by one Maxwell stress tensor. Problem is the exact formulation of this tensor is a debate since over a century. So you see those names here, those years here. These are the three most famous models which are around, and for each of them you can find a paper which proves it or contradicts it. So it's up to debate in the physics world. But we will focus on the body forces. I will use the Einstein-Laub model for the next slide. And what we want to look at is the effect on the stresses in the vicinity of the crack tip that these body forces have. And for that I use the following numerical models, or the geometry of the classical Griffiths type crack in a rectangular plate. We have an impermeable crack, so there's no crack, electric or magnetic field inside the crack, which directly leads to no surface tractions at the crack faces, which we want because we want to have look at the result of the body forces. Again, the Einstein-Laub model is formulated like this. You have here permeabilities of vacuum and pipe material and the electric field. The material of this plate is dielectric and isotropic, which leads to two decoupled partial differential equations, which can be solved in series. So you solve this, you get the electric field, calculate the body forces, and then you solve the second equation. The loading will be an electric displacement here at an arbitrary angle psi. The first results will be for psi equal to pi over 2 or 90 degrees. And I used the open source FEM Phoenix for the simulations. Now let's look at the stresses at the ligament for electric displacement perpendicular to the crack faces. And what you get are such fields. Firstly, these are only the fracture relevant stresses, so you get no significant shear stress at the ligament. You always get, independent of the sign of the loading, so if it's like the field points in this direction and this, you always get a compressive stress. That's simply by trying. And via some dimensional analysis and some parameter studies, you can describe this, what seems to be a singularity. I have to say it seems because I can prove it numerically, of course, that it's singular. You get a behavior like this. So the compressive stress here is proportional to the crack length. The square of the load depends, of course, on the electric properties and follows a 1 over r singularity. That's what I get here. And yeah, that's the result of the body forces on the ligament in front of the crack tip. So what's interesting now is what will happen if we superpose a mechanical loading. So we have tensile stress and electric loading, and because the partial differential equations I showed you were decoupled, we can superpose this quite simply, like this. So this is a classical mechanical solution on the ligament, plus what we have seen before. So remember, the L is always negative, and this results in a shape like this, where you have a maximum stress at a radius R max. I named it here. Here's the calculations for them. This is how you can express them. And you have a radius of compression. So there's always, because this singularity is stronger, you will always have a radius of compression. So at a distance of the crack tip. So now these are qualitative views, so it's just a curve. let's plug some numbers in to get an idea how big this radii are and how big this maximum stress is. And for that I took some extreme values. So these are really upper bounds or lower bounds, so extreme values, which is the maximum what can happen in a dielectric. So we have an electric field of 10 million volts per meter, which is, most materials break down electrically at that, but it's just to be extreme. Typical permittivity of a dielectric, not a piezoelectric, but a dielectric is around this value. This is quite a lower bound for fracture toughness, and that I set equal to the K1 here. And the typical crack length, 10 centimeters, is really big. So these are really, really extreme values, and what you get is at least a maximum stress of 1 gigapascal at this maximum point here, and the radius of compression is at max 0.1 micrometers. And if you decrease this the load by 1 order of magnitude, which is still a very, very high electric load of 1 million volts per meter, the maximum stress increases by 2 orders of magnitude, and the radius of compression is already decreases by 4 orders of magnitude. And this here is 1 order of magnitude below an atom radius. So continuum hypothesis, very, very questionable. So what you get is a really small area where the body forces take effect. So we were the ligament till now. So let's look at the hoop stress around the crack tip to see if there's anything else happening, if you have tensile stress or something like that. But no, you always get, so this is the hoop stress around the right crack tip here, but it's the same as the left one, and in the near field of the crack. And I changed this angle here, this loading angle, to see if something changes, but you see the curves are qualitatively the same. They don't, the minimum here doesn't move. And the result is that it's independent of the one component of this loading. It's only the two component of this loading. And that's almost it. Just so you have seen it, the body force vectors we calculated, so these ones, to get an idea where these compressive stresses come from. This is the right upper quarter of this plate with the crack. It's rather chaotic. You can't see much, but if you zoom in on the crack tip here, there are way too many arrows, but if you zoom in on this crack tip, you see a radial field of just, the body force vectors pointing at the crack tip, which is not surprising, because the body force vector had the gradient of the electric field in it, times the electric field, and of course there's a singularity here, and that's what will happen. And with that, I can summarize my talk. I've shown the influence of body force vector based on the Einstein-Laub model. You get the following near field with compressive stress, but still a very strong stress concentration. And future work will, of course, be to use this to see what happens when we have piezoelectrics. But then the PDEs will become nonlinear, and a lot more work. So with that, I thank you for your attention.
Thank you very much. So the talk is open for discussion now. No questions? Yes, please.
When you're using the example, extreme example, you have a crack length of 0.1 meter. If you go to realistic crack sizes, maybe 1 millimeter or even some. What happens with the stresses?
You can, the stresses, it's proportional, so L is proportional to the crack length and A. So basically what it's independent, I think. This is proportional to the, K is proportional to the square root of the crack length. So up here there will be A, and L is proportional to the crack length already, so it should be independent of it. But that's only the maximum stress, but the radii that's different.
Any other question?
I'd maybe like to add a comment. So I think the most challenging thing is to interpret the black curve here, because if you have compressive stress at the crack tip, that means that the crack will never grow, which doesn't happen in an experiment. So obviously there's something wrong. So one thing is maybe, as Alexander said, the continuum mechanics hypothesis is violated, just because it's a very small area, a compressive area on the crack tip. But we still think about how to interpret what we see here in terms of fraction mechanics. And the second thing is, if you apply another model, not the Einstein-Lauf model, but another model, you get a totally different behavior. So, for example, which one is it? We discussed it yesterday. It's a very new finding. So, according to one of these models, you only get tensile stress directly at the crack tip. So, these three physical models, which are contradictive,
One comment on that. These models, this is for electrostatics. In electrodynamics, you have time derivatives and so on. In electrostatics, this one and this one is zero if the material is isotropic. So the tensile stress was for an anisotropic material, which where I used the Abraham model. So there's a lot of back and forth when you look at papers and you have to ask a physicist.
Okay, so then the question is, how do you relate to the experiments?
Yeah. If you need experiments, but
so if you have totally contradicting predictions, so what happens in reality?
yeah, that's the challenge. That's the question.
Okay. Okay. Any other question? It seems to me that you should be able to at least to measure something and then to reinterpret it in the
There are experiments in literature with oil drops.
Okay.
So they impose electromagnetic fields on oil drops and see how they deform, and then they make calculations. And again, depending on what you look at, different of these models are partly applicable and partly not.
Right.
Still contradictory.
Okay. Any other comments or questions? If not, thank you again. Thank you.